Hello everyone, and welcome back to an L582 Modeling and Control of Electric Machines and Drives. In the previous lectures we start talking about the per-phase equivalent circuit modeling of a three-phase induction motor. As we used to do with all kind of machines, the per-phase equivalent circuit is the best way to go with trying to predict the performance of the machine, and we derived this equivalent circuit for the induction machine, so you can review it if you don't remember where or just how we landed out this shape of equivalent circuit. So it's actually the same circuit here, but rather than just having R2 over S, which was called the dynamic load, or just the R2 over S, that's all, we can separate it to two parts, R2 plus R21 minus S over S. So we can have R2 separated, which is the internal resistance of the rotor winding per phase, obviously, and having R2 1 minus S over S, what we call your dynamic load. So this looks almost like the equivalent circuit of a transformer, because like we said, the induction machine theory of operation just looks like a transformer but with a moving secondary winding. So the rotor here acts like the secondary of a transformer, but because you're having this rotor can rotate, so it's a rotating secondary winding. But like we said before, we cannot use such an equivalent circuit to model any kind of machine unless we make it unique for this machine. And this by determining the equivalent circuit parameters related to a certain machine. So this equivalent circuit, like you see in here, can represent any three-phase induction motor. So what makes it describe a certain machine under your hand is because those parameters R1, X1, R2, X2, and RC, XM, those 6 parameters, if they relate to a certain machine, so this circuit describes this certain machine. How to do this? By testing it in the lab. Okay, so we talked last time about the power flow diagram and just went around it, and then landed to this determination of equivalent circuit parameters. We recall lab testing of the three-phase induction motor to determine the equivalent circuit parameters of certain machine, and then we can use the equivalent circuit with these parameter values to predict the performance of this certain machine. Like we said last time, we do 3 kind of tests to find out those equivalent circuit parameters, the 6 parameters we want. Okay, those 3 are the DC test, no load test, and locked rotor test. Okay, like we have did before with the synchronous machine, if you remember, we did the DC test, the no load test, and the short circuit test. Okay, so they look like the same. The whole difference here is you're talking about a motor rather than talking about the generator of the synchronous machine. So we started talking last time about the DC test. This test, we use it to find R1, which is the per-phase resistance of the stator. Okay, so how to do it as a procedure, like we said last time, I'm just reviewing this in a hurry. We apply DC voltage to any 2 terminals of the stator winding and measure the voltage and current. Why I say this? Obviously, if you have all the terminals of all the 3 phases out, so you can access each single phase alone. Okay, like what we have in our lab with synchronous machine. So we have just the 6 terminals of the stator phases out, so we can just pick one of them and apply DC voltage to it and measure the voltage and current, divide them, the voltage by the current obviously, and you find the resistance. That easy. But what about if you don't have all the terminals out? Rather, I like the typical condition is just you have the 3-phase winding internally connected like Y or delta, and you just have the 3 terminals, the line terminals out. Then you don't have a separate phase just to measure its winding. Okay, in this case you do this, you just pick any 2 terminals and just apply DC voltage and measure the voltage over those 2 terminals and the current moving through them. Okay, why we having DC voltage? Like we said last time, is just because like that we just having a 0 frequency, so we're getting out of anything else. So let me just draw you back the equivalent circuit and see what will happen under the DC test. Okay, so under DC voltage applied to stator, and it's very important to look at the equivalent circuit at these conditions each time. So that is R1, JX1, and those are your shunt elements, RC, JXM, and here the rotor representation, JX2, and that is R2 and R2 multiplied by 1 minus S over S. Okay? So what you have did here is you just applied a DC voltage here. Okay? Actually, it is not the same like what we have, because that's a pair phase equivalent circuit, guys, and that means we are applying a voltage to a single phase, but like we said, we cannot do this. So it is the same idea, just we are applying DC voltage to the stator. Okay, having DC voltage will just will just take you out all the reactances, JX1, JX2, JXM, every reactance will go out eventually. Okay, why this? Because like we said before, it is just having something like that. It's just because it's DC, so its frequency equals 0, because that's DC, yeah? And the reactance X equals 2 pi FL, any kind of reactance, having a frequency equals 0, so you get out of all the X's, okay? The other thing to bear in mind is DC voltage on stator means there is no variation d phi by dt seen by rotor. Okay, remember what we said, where to come the voltage to the rotor is when it's cut by a time varying magnetic field, and this magnetic field in the stator now coming from DC source, so it's not time varying at all, and that means there is no induced voltage on the rotor whatsoever. Okay, so you don't have anything here. That means the induced voltage here over the rotor E all equals 0. That means you have a short circuit here because the voltage is 0. So it is just like that. Okay, guys? So that means E2 equals 0. That's E2. Because, yeah, actually the magnetic field, also the induced voltage happens at the rotor, happens when it sees a time varying magnetic field. And where this magnetic field comes from a DC source, and the machine does not rotate at all. So it is DC voltage and on the stator and no rotation. So you don't have any change in the magnetic field. The change in the magnetic field comes by two sources, guys. Number one, if this comes from an AC voltage, so it's changing by nature, like in induction machine. Or it comes from DC, which is not changing by nature, but it's rotating, like in synchronous machine. Remember, the magnetic field coming from the rotor of a DC of a synchronous machine comes from DC excitation, so it's not changing by nature because it's coming from DC source. But you apply rotation to the rotor, so the stator winding will see it as variable, its variation with time. Okay, here the machine will not rotate because there is no torque created here, because yeah, the whole theory of operation is not applicable here because you're applying DC voltage, not AC. So the machine does not rotate, and the magnetic field is not changing by nature because it's coming from DC now. So there is no induced voltage in the rotor, and that means, yeah, we don't have anything here to worry about. So the rotor winding here, the induced voltage in the rotor winding will be just 0, and that means you have a short circuit over the rotor, and you don't have anything else in whole of this circuit but your R1. That's why I'm saying, if you just measure the voltage and the current moving here, you can find this R1 easily. And that's why we're doing this, guys. So we applied voltage and DC voltage, and now everything just, if you just divided the voltage by the current, you get R1. Okay, but like we said, because we just haven't know the terminals out, so it depends on the connection of the three-phase winding of the stator. If it is Y connection, like on the left hand side, this connection will look like that, and the equivalent resistance seen will be 2R1, not R1, because we're just having two resistances in series. So if you want to find the actual R1, it will be just half of VDC divided by IDC. On the other hand, if you have a delta connection like on the right hand side, okay, so the equivalent resistance seen by the source here will be those R1 and R1 here in series like this, and the equivalent system is parallel with this one. So the equivalent resistance seen by the source, which equals VDC over IDC, will be 2R1 in parallel with R1, which gives you 2 by 3 R1. That's why if you want to find the actual R1, it will equal 3 divided by 2 multiplied by VDC over IDC. Okay, so it's just up to you. It was just up to the connection actually, if it is Y connected or delta connected. Okay, The other thing to just keep in mind, if you remember, like we said before, is the AC value of resistance equal 1.15 to 1.25 of R DC. Okay, so the measured value, just the value we found from here, that is R1 DC. That is R1 DC, because it's coming from DC excitation. Okay, the actual resistance when you apply AC voltage will be a little bit higher. If you remember, like we said before in the synchronous machine, that we call it the skin effect factor. If you don't remember that, just revise this lecture in synchronous machine, because we said as with AC excitation, the current tend to move in the outer space or the outer cross-sectional area of the conductors, and that's why the same wire will have a higher resistance for AC current than for DC current. And when you're applying DC voltage here, the resistance you're getting will be a little bit less than the actual one. Okay, like we said before, for numerical examples and problems to solve in exams, if this factor is not given for you, just ignore it. Just, yeah, because it's not a big difference like we see in here. But if it's given, that should be happen, and for typical conditions, you should just accounting for this skin effect factor by having or just maximizing the resistance you found by a factor from 1.15 to 1.25. Okay, so yeah, that is the first one. Okay, that is the first test to do it. Okay, guys, and this, from it we find the resistance of the stator winding. Actually, it's pair phase resistance. Bear that in mind all the time. Okay, that's okay. Now we have one test and found one parameter. It's the resistance of the stator winding, R1. So now let's move on to the second one to find more parameters, and it is the locked rotor test. Okay, guys, sounds good. What about this? Again, let's take the procedure here. Number one, put a mechanical brake on the shaft to lock the rotor. By that, prevent any rotation. So place a mechanical lock, anything to just hold the rotor in place to make it not rotating, and that means the speed omega m or nm will equal 0 for now. It's locked rotor. Okay, and that's where it's the name of the test came. It's locked rotor test. So we are locking the rotor, preventing from rotation. Okay, after this you apply 3-phase AC voltage. Now we no longer dealing with DC voltage, yeah? So let's apply 3-phase AC voltage to stator terminals. Okay, gradually increase the voltage from 0. So you start with a 0 voltage and gradually increase it until the stator current reaches its rated value. So this test happens at the rated value of the stator current. Okay, guys, that means you need to measure the voltage and the current of this machine, obviously, yeah? But keep that in mind. So let's work it at I stator rated. You can find the rated value from your nameplate, like we said before. From the manufacturer nameplate that been stamped on the motor body itself, you can find it. Obviously, if you on the lab, you will find this information on your lab panel, but on actual machine you will find it stamped, or just, yeah, you'll find the nameplate of the machine stamped on the body of the machine, and whether you can find this value for the rated current by the manufacturer. So you just gradually increase the voltage and look at the current. Okay, keep that in mind. because that's very important. Okay, locked rotor condition simulates the maximum load imaginable. Okay, now you're imagining you're placing a very, very heavy load, the maximum load that can be put. Okay, it is very high enough to prevent the rotor from rotate anywhere. Okay, that means, guys, a very high current will pass in the winding even for very small voltage. And that's why I'm saying start from 0 voltage and very slowly, gradually increase the voltage applied and lock the current, because this rated value of the current will happen at very small voltage. Okay, so don't even think about start by the rated voltage, because you will burn the machine winding. Okay, now you're locking the rotor. It just looks like a short circuit on the synchronous generator back. If you remember the short circuit test and the synchronous generator, did the same here. It's almost like short circuiting the machine by locking its rotor. So a very high amount of current will move through the winding even with a very small amount of voltage. So just look at the voltage. It's now a really dangerous test over the machine. Okay, so yeah, it has to be monitored. Okay, for number 3 now is measuring. So measure the stator line voltage, current, and active power. Okay, so already measuring the voltage and current, so you know, yeah, so all the time you're monitoring the current like we said, and monitoring the voltage also to see how much it goes, and measure the power of the machine. And now you have everything you need in hand to proceed with all the calculations you need to find more parameters from this test. Okay, so understand how we can use this information to find the parameters in the circuit. Let's look again at the equivalent circuit under this locked rotor test. So that is my equivalent circuit again, R1, JX1, and here's your shunt elements, RC and JXM, and here's the rotor, JX2, and yeah, and R2 over S combined or separated like you want. Okay, so from it here, and let's look at what's happening specifically at locked rotor condition. Okay guys, so what's happening at locked rotor condition, because it's locked rotor, so the speed of the machine equals 0. It's the meaning of locked rotor, yeah? And meaning the speed equals 0, that means the slip is equals 1. If you remember, the slip equals ns minus nm over ns. So if the speed equals 0, so the slip equals 1 at no speed at all. Okay guys? And that means for now that RT over S, this guy, R2 over S, will be very high. Now is just very small, sorry. Why? Remember when I said before that the typical value for the slip is very low. Okay? It is in fractions of 0.02, something like that, almost. Okay? So the actual speed nm of the machine is very close to the synchronous speed. That means the slip value typically is very, very small value. And this typically means that R2 over S will be very high, because yeah, the denominator S is very small typically. But in locked rotor condition, the slip now equals 1, not equals very small fraction like 0.02, 0.05, something like that. So that means now R2 over S is gone very small than usual. So it is very small, or very smaller than usual. Okay guys? And like you've seen here, look at this. From this equivalent circuit is the total impedance of the rotor, which is R2 over S plus JX2, okay, is connected in parallel with this shunt element, okay? It's just the circuit like it's saying here, okay? And to keep that in mind, the shunt elements RC and XM are very large compared to R1 and R2 and and X1 and X2. That's how the machine works, guys, okay? So the RC and XM is usually very high values. Typically, that's the actual machines will work like that. And it makes sense because it's a shunt element here. So the current is moving here. It's basically going to magnetize the core, and it's for the core losses. So it's typical wise logically to be very small, and that will not happen unless RC and XM are very high values, okay? So that's the whole point of that. So to keep that in mind, now we have R2 over S is very small and RC and XM is very large. Now recall your just basic information about the electric circuit. If you have two resistances or two impedances connected in parallel, one of them is very small and one of them is very large, okay? The equivalent of them will be much closer to the smaller one. That is how the electric circuit works. So if you have a very large resistance connected in parallel with a very small resistance, the equivalent of them will be almost equal to the very small one, and that means you can ignore all of this large impedance, okay? So this is RC and XM are in parallel with R2 over S plus JX2, which now is very small because the slip equals 1, okay? So we can ignore RC and XM at all for this specific condition because S now equals 1 for the locked rotor condition. And that's what we meant from the beginning. We locked the rotor to maintain the slip equals 1, so to make the resistance of the rotor is much higher than its usual value, and now that means the whole shunt elements representing the core, RC and XM, can be ignored. So for this condition, for the locked rotor condition, just for the locked rotor condition, RC and XM can be ignored because the equivalent impedance of its parallel value with the much smaller R2 over S plus JX2 at this slip equals 1 almost equals the smaller impedance, okay guys? So how this happens now? So now you're looking at this to be just R1 and JX1 and the rotor JX2 and R2, and I'm not saying R2 over S because now S equals 1, okay guys? So here the voltage applied, what I would call it V locked rotor, LR, and the current moving here will be I LR, I locked rotor, okay guys? Keep that in mind, by the way, this is the rated current, so we're doing this test at the rated current. Again, why are we doing that at the rated current? It can be done at any current, yeah? But we are doing it at the rated current because that is the typical condition where the machine works at, guys. So the machine typically works at its rated condition, and it's just the rated current moving in its winding. So if you want to find the actual equivalent circuit parameters from the test, you try to place the machine at the same condition that it should be working actually in the field. Okay guys, so this can be done at any kind of just any value of the current, but we like to do it at the rated value because it is the typical working machine's current. Okay guys, so we're trying to be just simulating the actual condition work of the machine. Okay, keep that in mind because that's important. I can give you this problem and do not give you how much current moving in the machine in the locked rotor test, and it's not a missing data because you should note for yourself that the locked rotor current equals the rated current, so you can just lock out the rated current of the machine and take it and use it. Okay guys, so yeah, keep that in mind. The current moving in the machine for the locked rotor test equals the rated current of the machine, which can be found on the machine's nameplate or can be found on the ratings information in any numerical problem. Okay guys, good. From now on we can just see what's happening. Now you know how actually the circuit looked like at the locked rotor test. So this locked rotor test equivalent circuit. Okay, from now you know that for any kind of circuit, P locked rotor will equal 3 I locked rotor squared times the resistance. You have here all the resistances and reactances are in series, so the total resistance will be R1 plus R2. Okay, that is how much power going to the circuit, guys. Okay, P locked rotor here is measured. You already measured it in the test, so you know it for yourself. And I locked rotor is also measured. You measured it for the test and it equals the rated value. Okay, don't forget the 3 because it's 3 phases. Okay, R1 is known from DC test. We have done DC test before to find R1, so everything here is known except for R2, so you can find R2 from here easily. Okay guys, so yeah, you found the measurement for the current and power and you can use it directly to find R2. Now it's easy. Now that's the second equivalent circuit parameter we found in our hand. Okay guys, and then we move forward to find what? So you have here P locked rotor like we said, and V locked rotor and I locked rotor. You can use them to find Q, so that is Q locked rotor. How to find it from here? Easy enough. Go to the equation. P locked rotor equals 3 V locked rotor I locked rotor cosine theta locked rotor. That is just how the power works. Yes, and you know everything here. You know P, V and I, they're all measured, so you can find theta from here easily. Okay guys, and here is your power triangle. That is the P locked rotor, Q locked rotor, and that is theta locked rotor. Yeah, so tan theta locked rotor will be basically Q locked rotor over P locked rotor. So you can find Q locked rotor easily by multiplying P locked rotor by tan theta locked rotor. Yeah, so now you know Q locked rotor for yourself. That easy? Yeah. And actually, if you can measure the Q in the lab, you can do it. You can measure it. But if not, that's fine. You can calculate it like that. And you know that Q locked rotor equal from this, the Q goes in this circuit for the X's. So the P goes in the resistances and Q goes in the reactances. You know that. You have two reactances, X1 and X2, in series for this circuit. So the Q will equal 3I locked rotor squared X1 plus X2. Yeah, Q locked rotor here is just calculated. We have just found it here. Yes, I locked rotor is measured. You know it. Okay, so this is known, this is known. That means you have X1 plus X2 together here you can find. So from this I can find X1 plus X2. Okay, so X1 plus X2, obviously for the locked rotor condition, will equal Q locked rotor over 3I locked rotor squared. Okay guys, so now you have X1 plus X2. That's good. But before moving on, keep that in mind. That's again very important to keep in mind, is Let's look back again. Like we said, we're trying to have the same working conditions of the machine in the typical way, okay? So what are the typical frequency of working of the rotor? Yeah, typically the frequency of the rotor circuit is very small. Remember that? Because the frequency of the rotor circuit equals S times F of the stator. I know this S, the slip, is very small, and that's why the frequency of the rotor circuit is very small. Like I said last lecture, it will find it in the range of 5-6 hertz, something like that. It's very, very small, okay? But in this condition, in locked rotor condition we are making here, FR will equal Fs. Why? Because the slip equals 1. So it is not the actual condition for FR. Now FR is very, very higher than it should be, actually. So if it is applicable, we do the locked rotor test at 1/4 of the Fs, okay, of the rated condition actually of it. So if you have a source that can be controlled to control the frequency of it, not just the actual source coming from the supply, from the grid. So if you have a source that you can control its frequency, so it's typically done at 1/4 of the frequency. In our lab we don't have that, so we just ignore this. But if you have this capability to do it, just do it. It's much accurate if you can do this like that. Okay, so if you do it like that, so if you do it as 1/4 of the frequency like that, so after you get x1 plus x2 like this from the locked rotor test, which is done at 1/4 of the frequency, so you need to find the actual ones. So x1 plus x2 at the rated frequency will equal x1 plus x2 combined at the locked rotor frequency, the frequency you've rated the test at, multiply by F rated over F locked rotor. Okay guys, so like I said, if you do this test at a different frequency, which is typically 1/4 of the actual frequency, so that means the x's you just found here is just made at much reduced frequency. So you need just to transform them back to the actual frequency, and you know x is just directly related to the frequency. X equals 2 pi FL. Okay, that's why we do this direct relationship here. We find the actual one by multiplying the measured one, those or just the calculated one. We just found them up there, those guys, x1 plus x2 locked rotor. You multiply them by this ratio, F rated over F locked rotor. Okay, so this ratio typically equals 4, because like we said, F locked rotor most of the time we make it at 1/4 of the F rated. Okay guys, again, if you don't do any change in the frequency like we did in the lab, so all this ratio will be equaling 1. Okay, so yeah, if you just had to perform this, or you just have a variable frequency supply you can use and use it at 1/4 of the frequency just for more accuracy, then you have to just transform back the reactances to the rated frequency, because that is the typical condition of work of the machine. The machine works at 60 hertz, yeah, not at 15 hertz, which is 1/4 of the 60 hertz. But like we did in the lab, we didn't change in frequency, so you don't need to do this transformation, because basically F rated equals F locked rotor, because both of them were done at 60 hertz. Okay. Okay, now we find x1 plus x2. Okay, but we want to separate them. We want x1 alone and x2 alone. Okay, so separation of x1 and x2. This is done actually by experience based values. we don't have an obvious way to find it mathematically or to measure it, so we just rely on experience here. So over the years, guys, the manufacturers of the induction machines, along with all the designers of it and all that stuff, have just figured out or just measured hundreds and hundreds of different machines and just landed out of an experience-based values that you can just use actually to find this. And this landed with this table, if you look at, and you can use it. So it depends. So yeah, for the machine, typically the machine, so if it is a wound rotor machine, if the machine has wound rotor, then x1, x2 is 50% and 50%. That means if you find x1 plus x2 to be 10, for example, that means x1 equals 5 and x2 equals 5, yeah? For those guys here, you are talking about the squirrel cage rotor, which is the most widely used one. And these different classes, A, B, C, D, is different design values. We'll be talking about it in a bit. Okay, so you'll know, and you will know this from the manufacturer, and you find it from the nameplate of the machine. You'll know which class is this motor, so it's different designs actually. Yeah, it's the same working principles, but a different way of designing the machine. So you know which class you're dealing with, and you just find it from here. So for class A, it's 40% X1, 60% X2. The same for class B. And class B actually is the most commonly used one most of the time here. So yeah, if I don't give you any class, just assume it's class B. So that is the fundamental to deal with. Class C is 30%, 70%. Class D is 50%, 50%. So yeah, if it's a wound rotor machine, I don't need to give you anything. You know that's 50-50. If it is square cage machine, mostly you need which class of it. So you can just use this table to find X1 and X2. Okay, guys? And again, that came by experience. It does not have any mathematical derivations, just the experience of the manufacturers and designs of these machines. Okay? Sounds good. So for the second test, the loop rotor test, we come here to find another guys. So from this test, you can find R2, X1, and X2. And I've already found R1 before, so we have R1, R2, X1, X2, and the rest is just RC and XM, and this we need another test. Okay, guys? Okay. So let's jump over to the third test, which is the no-load test. So the third test is the no-load test, okay? So let's take again the steps of performing the test. Number one, obviously remove the lock on the rotor, okay? We're not locking the rotor anymore. Number two, apply the rated voltage to the stator terminals. So this test is done at the rated voltage of the machine. Again, why the rated voltage? Because that is a typical condition of the machine working at, okay? Now we need the no-load test, so that we will just let the machine run freely but without applying any mechanical load to the shaft. Okay, guys? So you're applying the rated voltage to the stator terminals, okay? And let the machine rotate without any load attached to its rotor, okay? So if there is any load attached to the machine's shaft, you just decouple it from the machine and just leave the machine alone and apply the rated voltage to it and let it run freely. Okay, guys? Number three, do your measurements. So measure the power, voltage, and current. Again, you don't need to know the voltage to do, because the voltage here is the rated voltage. So I can give you an example of just a numerical problem like this, and I don't give you the voltage for the Norwood test, because you know it yourself, it should be at the rated value. That would not be a missing information. Okay, guys? Again, under these circumstances, okay, what the machine will be looking like, okay? So for this condition, we need to know which actually circuit we are dealing with here, okay? So yeah, it's just to look at from here. Let's again look at the equivalent circuit. All the time look at the equivalent circuit. How much will we looking at? Okay, R1, X1, that is RC, JXM, and that is, sorry, that is, yeah, JX2, and that is R2 over S. Okay, under the no load condition, you know for yourself that for no load condition, guys, yeah, Nm is less than the synchronous speed. The machine rotates now and rotates at less than synchronous speed, but Nm very close to Ns. Okay, you remember this before. So Nm is very, very close to the synchronous speed, and with the increase in the load, Nm starts reducing. So Nm starts very high, almost equal to the synchronous speed. So Nm almost equal to the synchronous speed, because you are dealing with no load, yeah? And with the increase in the load, Nm starts reducing, starts to be lower and lower. But we are dealing now with the no load conditions. So Nm almost equals Ns. Yeah, it's a little bit less than it, but it's almost equal, okay? So the slip, which equals Ns minus Nm over Ns, will almost equal 0, because, yeah, Nm almost equals Ns. Okay, guys? So if S almost equals 0, so R2 over S will be very, very high. Now, R2 over S is very high. Compared to the log-neutral condition, with R2 over S is very small, because S equaled 1. But now S almost equals 0. So it's a denominator to be 0. That means R2 over S is very, very high. So it's now swinging in the other direction. Remember, here are 2 over S, and compared to this, now the very big one is this one. So this one is very big. Okay? And again, those two are just connected in parallel. And that means now it is a different way. Now R2 over S plus JX2 is the one to be ignored. Okay, guys? Because now it's very, very big compared to RC and JXM. So again, the equivalent of them paralleling together will be almost equal to the smaller one, which is now RC JXM. So R2 over S is now very, very high. So R2 over S plus JX2 together can be ignored here, okay? Because they are parallel with much smaller one compared to them, which is RC and XM. So now you can find it like that, R1 and JX1, and now it is RC JXM. Okay, guys? That is if you are using the exact equivalent circuit. Remember, the exact equivalent circuit is just RC and XM. This one, that is the exact equivalent circuit. Okay? But you remember what we call the approximate equivalent circuit, where you can just find, so the approximate equivalent circuit is like that, R1 JX1 and just JXM in the middle here, that is JX2, and that is R2 over S. Remember, for the approximate equivalent circuit we don't have RC, because we are just assuming that the core losses represented by RC usually is just a constant loss lumped with the friction and windage losses or rotational losses at the end. So we don't represent it by RC. That's why we call it the approximate equivalent circuit. It will be just like the same here. So you'll also ignoring R2 over S plus JX2 when compared to JXM, and the approximate equivalent circuit will be just looking like this. Okay, so we talked about the difference between the approximate equivalent circuit and the exact one in much details on the last lecture. If you don't remember, please review it back, okay? So for the other two tests, the DC test and the locked rotor test, it doesn't matter which circuit you are dealing with, because we were just ignoring everything, ignoring the whole branch, RC and XM or XM, it doesn't matter. But for this test, because we are now dealing with the shunt elements RC and XM, it's important to know if you're working with the exact equivalent circuit or the approximate equivalent circuit, okay? Because either you have RC or you don't have it. So if you're dealing with the exact equivalent circuit, you will have RC represented in the circuit. If you're dealing with the approximate equivalent circuit, and that means you're just don't have RC in the circuit, and you just then the core losses is just a constant loss lumped with the friction windage losses or the rotational losses. Okay, guys? So that's different, and that means you need to just deal with each one alone. Okay, so I'm gonna start here by dealing with firstly the approximate equivalent circuit. Okay, in the approximate equivalent circuit, there is no RC, okay? The core losses are assumed to be constant with the load change. So we don't have RC. Okay, guys? So for this, the no load condition, like we said, that is R1, JX1, and that is will be just JXM, because we don't have RC. Okay, guys? And for this, that is the voltage V no load, and the current going here is I no load. Again, we are dealing with the no load condition, because that's our test. Okay, guys? So now we can deal with the circuit. Again, we'll lock P no load from the circuit. That circuit here just doesn't have but one resistance, which is R1 here, yeah? So P no load will equal 3I no load squared times R1 from the circuit, yeah? But keep in mind, the power that goes to the no load of the machine is actually going to the no load losses of the machine. So from here, you're just dealing that is a copper losses and the R1, it's just the 3I square R1. But there's two other power losses that are not represented in the machine now and still exists. Remember the power flow diagram of the machine? Now you have two other losses that's not represented here, which is the core losses, P core, and the rotational losses, P rotational. They exist because the machine is rotating and it has an AC magnetic field. Magnetic field comes from AC supply. So you have core losses and you have rotational losses, but they are not represented in the equivalent circuit, okay? But you don't ignore them because they exist, okay, guys? That's the thing. If you remember when I just illustrated this last lecture, is the equivalent circuit represents all of the losses we have in the machine by resistances except for the rotational losses. That happens in the exact equivalent circuit where you have RC in the circuit representing the core losses, but you don't have anything to represent the rotational losses, so don't ignore it. It's there, but it's not represented in the equivalent circuit, okay? If you're dealing with the approximate equivalent circuit, like here, you are assuming that the core losses is also not present in the equivalent circuit. You don't have a resistance to represent it. You don't have RC. But it's over there. You do not ignore it. Okay, guys? So the P no load is 3I no load square R1 plus P core and P rotational. Those two are not represented in the equivalent circuit here, in the approximate equivalent circuit. Okay, so we add them by hand. So P rotational and P core not represented in the approximate equivalent circuit. Okay. Okay. That's good. So from here you can just use this one directly, not to find anything but to find those guys. Okay, so now just assuming that P rotational and P core are lumped together. Okay, so you can find them together here. So P core plus P rotational equals P no load minus 3 I no load square times R1. Okay, this one is measured and the current is measured, and R1 found in DC test. Yes, so everything is known here, so you can find those losses, the P core and P rotational. It's how you find your losses here. Okay guys, so yeah, we didn't find a new thing, a new equivalent circuit parameters, but we found the core and low rotational losses. And you don't need to separate them here, because basically you're just assuming both of them are constant and they're just attached together, so no need to separate them. Okay guys, so that's how we can find P core and P rotational together here. Okay, and using the same way, by the same mean, P no load will equal 3 V no load I no load cosine theta no load. Yeah, so the same way you find Q no load, the reactive power, equals P no load tan theta no load, because everything is known here. P no load, V no load, and I no load, they are all measured, so you can find theta no load easily. You just apply it here to find Q no load. And Q no load from this circuit here, you just have X1 and XM in series, and the Q goes to the X's. So this goes to 3 I no load square X1 plus XM. Yes? Q no load is just calculated here. And by the way, you can measure it if you can measure Q in the circuit. So it's up to you in the lab, yeah? And I no load is just measured. You know it. X1 is known from Lec23 test. Already found it, yes, before. So everything is now just to find XM. So XM here can be found. Okay guys, and like that we found all the parameters we need. Remember, we're dealing here with the approximate equivalent circuit where there is no RC at all. Okay, so you found all the equivalent circuit parameters, and you even found the core and rotational losses together from this test. Okay guys, what about if you have the exact equivalent circuit and have RC in the circuit? That means the core losses are not lumped together with the rotational losses, but they are separated, and you need to separate them and find each one alone and find RC. That will be just continue talking about the next time. Thanks so much guys for joining me today. Take time to review this. There's a lot of tricks here that you can just lose your way and make mistakes in the exams, and we don't like that. So just have a time to look at it and review the tutorial that will be posted just after this lecture. It will be a direct numerical example over those 3 tests. It will be much help to make these principles rigid to your mind. Okay, thanks so much guys for joining me today, and I hope to see you next time.